Well, greetings out there in YouTube land, and welcome to today's big video in which we will add a tremolo effect to the high wattage single-ended amp that we built in our last three-part video series. I will cover step by step all of the physical modifications, the circuit alterations, and finally give you a thorough audio test so you can judge for yourself just how well this tremolo effect worked. The physical alterations required the addition of an additional 9-pin tube socket for our 12AX7 oscillator tube, the addition of a 25K intensity pot with the calibrated ring and chicken head knob. And then for the speed control, I actually ran out of space, as you can see, so I resorted to a stealth speed control here on the side with a small knob, and this connects to the 3 megohm potentiometer with which we will alter the speed of our tremolo effect. I personally think that the addition of this 12AX7 tube and the intensity control give us a much better balanced chassis without those two open spaces that we originally had. So besides the benefits of the tremolo effect, we also get improved cosmetic appearance. Now this should be very helpful to those of you who constructed your own version of this amp. You may want to add the tremolo effect. And to those who have built their own amplifier projects, not necessarily this one included, this will show you a nice simple way to add tremolo to virtually any amplifier that you've built. So let's hope then that this is of common interest and that it will be a very worthwhile experience for you to spend the next half or 3/4 of an hour with your old uncle and his furry friends. Now, before I get into the physical modifications and how they look from above and beneath the chassis, let me discuss with you the schematic that I created to add the tremolo, I thought, in a rather simple and straightforward manner. Also, it's quite effective, as you will see, so I really think it's kind of a win-win design. This is the schematic that I drew up for the tremolo addition to the high wattage single-ended amp. Those of you familiar with Fender schematics, I think, will recognize this as being very similar to the tremolo circuit in the Vibrochamp amp. It functions by modulating the cathode bias of the first triode of the preamp tube in our existing circuit. V2A is the first triode of the 12AX7 oscillation tube that I added to the circuit. We see that it is energized with 170 volts, the B plus, to its plate. I will explain later and show you in the circuit exactly where I got this amount of voltage supply. Now, I have already posted a couple videos showing in detail how different types of tremolo circuit work, but I'm going to go back and give you now a sort of a superficial overview. And those of you who want more detail, please go check my video list and watch those specific videos. For those of you who would like just the quick overview, here we go. Now, I want to draw your attention to the fact that we have 3 capacitor resistor pairs. We have one here, we have one here, and we have one here. And the effect of these pairs, depending on the value of the capacitor and on the value of the resistor in the pair will alter the phase of the signal that passes through it. It will also delay it. Now, why is that important? Well, if we didn't alter the phase of the signal in the loop, the signal we know coming from the plate is of opposite phase to that on the grid, we would have a self-canceling negative feedback loop, which would accomplish nothing for us. But instead, due to the value of this capacitor and this resistor, the signal here will have its phase altered by 60 degrees, 60 degrees, and 60 degrees, giving us a 180-degree phase shift for our signal, which means when it gets back here, it is in phase with the grid signal, not out of phase. Therefore, we have created a positive feedback loop. Now, the reason that the delay is important is that if we allowed the signal to leave here and go unimpeded back to the grid, not only would it arrive out of phase and therefore be a negative feedback, it would also arrive so fast that we wouldn't have any sort of rhythmic slow oscillation that we're looking for. And the simple fact is that each of these resistors affects or alters or controls the charge and discharge rate of the capacitor in its pair. So when the signal hits here, it will charge this plate, and in so doing induce a charge on this side, and the speed at which it can do that will be controlled by the resistor in the pair. So we're going to slow down that signal so that it comes back about 2 to say 10 or 12 times a second. So if we crank this resistor up to maximum resistance, the signal will come through here and be very, very slow through this junction, and then it will get its 60-degree reversal here, 60-degree here, and it will arrive significantly delayed. With it set at 3 meg to ground, the charge and discharge rate will be very slow, and our tremolo will be at around 2 cycles per second. If we crank this resistance way down to say 500K or even all the way down to 100K, then it will recharge very quickly and will have a much more rapid traverse of our oscillation loop, and we will have a rapid tremolo. So, 2 points to remember. The signal has its phase reversed 180 degrees in the loop, and it also has its return rate delayed a varying amount depending on the value of this resistor, or you can also change the value of one of these capacitors. The 0.01 can be changed to a 0.02, and that will slow it way down because a 0.02 recharges at a slower rate than a 0.01. So you can affect the rate of oscillation either by altering the 3 meg variable resistor pot or increasing one of the 0.01 microfarad caps to 0.02. Okay, oscillation loop specifics aside, we see here that we're going to draw some of our signal out of the oscillation loop and send it over here to the grid of the second triode of the oscillator tube, the 12AX7. we see that it receives 340 volts of B plus to its plate, and as I said, I will show you how and where I get that in the circuit. And this is actually a cathode follower. We're not going to take the signal out of the plate, we're going to take it out of the cathode itself, which means that the signal will not suffer much voltage drop as it proceeds over here to the cathode of our preamp tube, the first triode. Okay, so we use a cathode follower. We take our signal from the cathode and we run it through a 68K fixed resistor to the wiper of the 25K intensity pot. We do this to reduce its intensity somewhat. That was perfectly appropriate for the vibrochamp circuit, but I found in this circuit that the signal was still too strong and it was overpowering the cathode of the preamp tube. So I used trial and error in one of those variable resistance boxes, and I came up with 15K ohms in this position to further reduce the strength of the signal that I fed into the cathode of the preamp tube. Also notice that this is the same cathode that our NFB loop feeds into. The Tremolo oscillation loop feeds in before the cathode bias resistor. The NFB loop feeds in after. Also, we still have 47 ohms to ground here, which is the same value as in the vibrochamp circuit. Now, if a couple notes I put here, if you want to have a pedal to turn the tremolo on and off, then I suggest that you follow the vibrochamp schematic, and the pedal here will either make or break the ground for this resistor. So you would simply wire your pedal in here, and like I said, look at that vibrochamp schematic and it will show you very clearly how to do it. I don't have a pedal on this particular application. Number two, both the 3 megohm speed variable resistor and the 25K intensity pot were recommended to be reverse audio. And those are hard to find sometimes. I had a heck of a time. It's hard enough to find a 3 megohm resistor, or variable resistor. So I decided I'd just go ahead and see if it made that much difference. So I put in audio pots in both places, and they work just fine. So my footnote here is that reverse audio is recommended, but it is not essential. So I think that covers the design, the function, and the logic behind the tremolo circuit that I'm going to insert into the high wattage single-ended amp circuit. And I hope that my explanation makes it clear for you. Well, it's time for logic to end and grim reality to be faced. And here's the most dreaded moment and when dealing with a painted finished amp, is to install another 9-pin socket. I have to drill a 7/8 inch hole right here in the chassis, which scares me to death. After moving all the wires that are underneath the surface of the chassis, I created a sterile operating field here, and then I've drilled a 3/8 inch hole, which is as high as I can go with conventional drill bits. Now I'll have to go with a step bit to open this up to 7/8. I was able to drill the hole without any harm to the surface of the chassis, and I have installed another 9-pin socket. And here we see the newly installed 12AX7 oscillator tube installed on the chassis, right beside the output tubes, which could be either the KT88 single tube here, or in this case, the two 606GC parallel output tubes. The next step was to drill a hole here for our intensity control, which was a 25K pot. It's this one right here, and all I had to do was drill, as I recall, a 3/8 inch hole, and I put in a matching value ring as I had on the front here for the volume and tone controls, and a chicken head knob. So there is our intensity control. And next I had to come up with a way for the speed control, and there's really no place here that didn't look crowded or kind of out of place. So I went to the side and kind of put in a stealth knob here that controls the speed pot, which is the 3 megohm potentiometer, and it's the same 3/8 inch hole in the side over here with a small knob that can be rotated then to control the speed of our oscillation loop, and thus the speed of our tremolo effect. I flip the chassis over and we see here the newly installed oscillation tube positioned right here. The first step, let's go into where I got the B plus to properly energize the plate of both the first and second triodes of this oscillation tube. Here is pin 1, which is the plate of the first triode of the oscillation tube. To get its 170 volts of DC power, I ran a wire from the third node of the power supply through resistance to pin 1, and the resistance that turned out to be correct in my case was 488K ohms. Now this value is not an absolute, because depending on your power transformer, your power supply wiring, and all, yours may vary, but that's how I found the exactly correct B plus supply for pin 1. Now to get the 340 volts of B plus for pin 6, which is the plate of the second triode of the oscillator tube, I ran a wire from the second node of the power supply through a 27K ohm resistor into that pin 6, and the end result was almost exactly 340 volts as the schematic suggests. Now for the oscillation loop between pin 1 and pin 2, I had to come over here to get the proper room, but here you see the 0.01, 0.01, and 0.02 microfarad oscillation loop capacitors that are both connected over here to pin 1 and 2 of the oscillator tube. Pin 3 is the cathode of the first triode of the oscillator tube, and as you can see here, it is cathode biased with a 4.7K bias resistor and a 25 microfarad at 50 volt bypass capacitor. Pins 4, 5, and 9 are the 6.3 volt filament voltage, which I simply jumpered here from the preamp tube over to the oscillator tube. We've already discussed the plate supply here to pin 6. Pin 7 is the grid of the second triode directly connected to the plate of the first triode. And finally, we have pin 8, which is the cathode output of the second triode of the oscillator tube. We bring it over here through a 68K resistor into the 25K intensity pot. We exit through a 15K resistor and then feed into a pin 8, which is the cathode of the first triode of the preamp tube. That was a little confusing. Let's look at it on the schematic. Okay, the output from the cathode of the second triode of the oscillator tube through a 68K ohm resistor. It's the wiper then of the 25K ohm pot. One side of the pot goes to ground, the other side goes through the 15K ohm resistor that I found was necessary to reduce the oscillation strength to this cathode. Otherwise it was kind of harsh and it was overpowering the tube, so I found by trial and error the 15K ohm resistor that then feeds the oscillation loop modulation into the cathode of the first triode of the preamp tube. Now the wiring of the speed control is very simple. Our 3 meg ohm potentiometer, which in this case is going to be used as a variable resistor, so only 2 of the lugs will be used. Okay, our signal will come in from the junction of the 0.01 and 0.02 microfarad capacitors in our oscillation loop, as we saw in the schematic, and it will come over here to one of the outer lugs, and then from the wiper of the potentiometer slash variable resistor will go through a 100K resistor to ground. And as said before, the 100K resistor is simply insurance against cranking this potentiometer down to 0 ohms and grounding our oscillation loop. Okay, so this prevents that from happening. Okay, we've talked about the physical alterations and all of the wiring and electronic considerations. Now let's flip this jewel over and see how it sounds with both the input of a signal generator and guitar. Using the trusty signal generator, I'm going to inject a 1 kilohertz tone into the input jack of the amplifier. I'm going to crank up the volume so that we can hear the tone clearly. And then I'm going to reach underneath and start to increase the intensity pot. There we go. That's at about 15, 25, 50. Nice and clean and good intensity. Now let's adjust the speed of the oscillation and the tremolo effect using our 3 meg pot here mounted on the side. It's about as fast as you need to go. And about as slow. So I think you'll agree that we now have a really nice Fender style tremolo installed in our high wattage output single-ended amplifier. But let's not trust the signal generator alone. Let's flip this over and get Jack and Missy to tune up the old guitars, and let's strum a few tunes through the amplifier using different settings of speed and intensity on our tremolo effect and see what you think. Well, now it's time for the audio demonstration of the tremolo effect. Jack and Mitzi have played 9 separate tunes here with varying amount of tremolo intensity and speed. I'm not going to tell you what they are. I think you can tell by listening. So without further ado, let's get started. As an additional feature, I thought I'd include a brief technical presentation here on how you can very easily test your tone controls if you have a signal generator. Now, the characteristics that we're looking for is that first, the treble control will provide us with nice, smooth, clean modification of the treble frequencies in that it will increase their volume without altering their tone or creating any sort of distortion. Likewise, with the bass control, that will get nice, smooth increase of bass frequencies and reduction of bass frequencies. At no time should there be any crackling or popping or anything that would necessitate either cleaning or replacing the potentiometers. The second important feature is that we do not want them to interact with each other. In other words, when I inject bass frequencies, I don't want the treble to have any effect on my bass frequencies. And conversely, when injecting treble frequencies, I don't want my bass control to alter them in any way. They have to be completely independent of each other. Now, this is the treble control. This is the bass control. I'm going to turn up the volume to where we can hear the 150 hertz signal, which is down in the bass range. I'm going to crank it up to where we can hear it clearly. Now, since that's in the bass range, the treble control should have little or no effect upon it. And it doesn't. Let's see if the bass control has much effect. We're going to go from 0. Wow. I hope you can hear that clearly with the camera microphone trying to equalize volume, but the increase is huge. So, at 150 cycles, my tone circuit responds only to bass frequencies with the bass control and does not alter the tone or volume at all when I rotate the treble control. Now let's try the higher frequencies. Next, let's inject a treble frequency of approximately 2000 hertz. Granted, that's at the bottom of the treble range, actually more like mid-range, but for the purposes of the test and our sanity, I try to keep the frequency down low enough where we can tolerate it. Here we go. First, let's see if the bass control has any effect. None at all. Now the treble control. I'm hoping that the camera volume equalization does not interfere with a tremendous increase in volume of treble frequencies as the treble control is turned upward. So conclusively then, we've proven that the controls are completely independent of each other and they provide a smooth increase in the appropriate frequencies without any noise, static, or induced distortion. In this case, this is the way it should turn out. Test your own amps if you have a signal generator and see, and I'm going to bet you that on some of them they will not perform like this one did. Okay, and in that case you can go in and modify your tone circuit and improve it and improve your amp's performance overall. Thus we see that this very simple and straightforward test can give you some very meaningful information about your tone controls. You could also do the same for your mid-range control if you have one. And it's way better than just kind of fooling around with a knob and saying, yeah, that sounds pretty good. It's much more scientific, if you will, and you can pick your specific frequencies to do your testing and really do a very rather sophisticated evaluation of the tone circuit of your own amp. I hope this is helpful and that you will find it useful in the future. As an added feature, I thought it might be interesting to use the trusty oscilloscope to visualize what's going on within the tremolo circuit. For our first demonstration, I will install the oscilloscope probe right here where the tremolo oscillator circuit is connected to the cathode of V1B, which is the first triode of the preamp tube. Now what we'll be looking for is how does the intensity adjustment affect the amplitude of the amount of voltage being applied here to the cathode to alter its bias, and also we'll see how our speed control functions to control the frequency of the modulation of the application of the oscillator signal to that cathode. Okay, so here you see our oscilloscope screen, and this is remarkably like an EKG in the hospital, really. Until there's some input, we'll be scanning for time across the scope on the x-axis, and now I will gradually turn up the intensity control on the tremolo. Now each of these squares is 1/10 of a volt, so as our trace rises 1 square, 2 squares, 3 squares, just multiply the number of squares times 1/10 of a volt. It will go upward and downward, and it will give you an idea of the amount of voltage being applied to alter the bias of that preamp tube. I'm going to have some tone in the background to give you both an audible and visual representation of what's happening. Now here goes some intensity being added, and as you can see, let's go to about 1/10 of a volt positive, and negative is being applied to the cathode of the preamp tube to alter its bias, and by doing that, altering its gain. Let me crank up the intensity a little more, and now we're at about a total of about 0.4 volts, the total excursion from peak to trough. If you count the number of beats that you see in one traverse of the screen, it will give you an idea of the frequency of the tremolo. Let me crank it up all the way. Wow, that's going to be, what, about 0.8 of a volt? 0.4 positive, 0.4 negative. Pretty stout input. Now I'm going to crank it back down. And the flat trace shows us that when the tremolo intensity control is down to 0, that well, I see a little bit of flickering there, but almost just a microscopic amount of our oscillator output will be applied to the cathode. Now let's watch the speed control in action. Let's get 0.2 here, total deflection, and I'll start cranking the speed control. We're going into fibrillation. Look at that. Extremely fast. Now we'll slow it down. To the minimum speed. Now, if you recall before, I mentioned that we could accurately measure the beat rate of our tremolo using the oscilloscope. Now, the vertical squares are voltage, and each one of those is 1/10 of a volt, but the horizontal squares are time, and each one is a half second. So we have a total of 5 seconds. We have 2, 4, 6, 8, 10 half-second squares. So the full passage across the oscilloscope screen takes 5 seconds. Let's count the number of beats that it takes for our signal here to traverse the screen, and then divide by 5 to get the beat rate of our tremolo at its lowest speed setting. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Probably around 15. 3, 4, 5, 6, 7, 8, 9, 10, 11. I'd say 15. So divided by 5, we have 3 beats per second on our tremolo. Now I can speed it up. It just makes counting the beats harder. But as you can see, at full speed, there's a whole bunch of beats per 5 seconds. For our next test, I'm going to attach one of the oscilloscope probes back here to the output jack of the amplifier circuit, and we will watch how our tremolo oscillator unit modulates the amplifier output of a 10 kilohertz signal. Here we have the audio output of the amplifier with an injected 10 kilohertz frequency signal from the signal generator. Now I have over here the seconds per division at 1 millisecond, so it's 1,000 times the 10 peaks you see, which show us that we indeed have 10,000 cycles per second. Now the tremolo is turned off, and the speed, of course, is down to as slow as possible. Let's see what happens when I start to crank up the tremolo, and then we will adjust the speed control. Now I'll start cranking up the intensity of the tremolo. Recall that the amplitude of the wave is indicative of the volume of the output signal. So let's watch what happens to that amplitude as we start to crank up the tremolo intensity. This is why we say that tremolo is a modulation of volume, not frequency. You see that the frequency is staying exactly the same. We see the same number of waveforms, but the amplitude is changing dramatically. In fact, we're down here at maximum intensity. We're down to where we're almost going to zero volume in the trough of our tremolo modulation. Let's go back up to a medium intensity, and now I'll start to alter the speed. As you can see, it's just going nuts. Okay, I'll slow it down here. And we'll go back to our slow, swampy tremolo speed. Probably 2 or 3 cycles per second. So here you see then a visual representation of the effect of the tremolo oscillator circuit on the output signal from the amplifier. We also see that here proof that tremolo is an alteration purely of volume and not of frequency. I'm cranking down the intensity to 0, and as you can see now, our output signal has stabilized and we have no tremolo effect. And for a visual representation of the relationship between the amplitude of the wave and volume, let me crank up the volume of the amplifier. Down, up, and you see that the amplitude is the only thing affected by the volume control. Also, I can pretty well emulate the tremolo effect with the volume control. Well, I guess that about does it for our oscilloscope evaluation of the tremolo circuit. It also brings us to the end of today's video, in which we covered the addition of a tremolo effect to our high voltage single-ended amplifier. I hope you enjoyed our video presentation and that you'll join us again in the future for additional postings from our channel. And at this time, I would like to thank all our Patreon patrons and PayPal contributors for their generous support of our channel, keeping us on the air for another month. Now, we do not monetize our videos, so our sole source of support are these generous individuals. If you'd like to join them, I'll provide links in the video description which will enable you to do so. I'll also provide a link in the video description to the schematic of the tremolo circuit that was featured in today's video. So as we bid a fond farewell, I hope you all have a great Thanksgiving, which will be in the next couple weeks, and an equally wonderful holiday season thereafter. Okay, so stay tuned, stay healthy, stay happy, and we'll see you again in the near future. Bye for now.